All right. Thank you so much, everyone, for coming. Before we start anything, let's begin with a brief prayer in the name of the Father, and the Son, and the Holy Spirit. Amen. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done on earth as it is in heaven.
Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation, but deliver us from evil.
Hail Mary, full of grace, the Lord is with thee. Blessed art thou amongst women, and blessed is the fruit of thy womb, Jesus.
Holy Mary, Mother of God, pray for us sinners, now and at the hour of our death. Amen.
Glory be to the Father, to the Son, and to the Holy Spirit.
As it was in the beginning, is now, and ever shall be, world without end. Amen.
Saint Jerome,
Pray for us.
Thank you, everyone, for coming. I was pretty disappointed we weren't able to do it from my home. It's much more enjoyable to do it in the comfort of one's home than driving down into D.C. at 6:45 on a Friday night. So I'm really grateful to everyone going through the weather and the difficulty of getting here. So we have Ed Trudeau, who's going to be our main speaker tonight, and also our natural philosophy and math teachers are going to be able to sort of reflect on their experience actually teaching the curriculum. Let me give you a little background on Ed. If you look on the bio of the website, it's one sentence. And I think it says something like, Ed is a board member at the St. Jerome Institute. And I looked at that today and I thought, that's not really accurate. And I called Ed and I said, hey, you don't have much on. He said, well, no one wants to know about me. I said, well, no, they actually do. So can you tell me a little bit? And he told me about himself, and it was very long. Very impressive background. So Ed Trudeau has his mathematics studies at Harvard University, where he received his bachelor's in math. He also has his master's in theology from Steubenville, his master's in computer science from Catholic University, and he's currently working on his PhD in computer science at Catholic University, specifically in the area of AI security. So he's got a lot of experience in these areas. He's lived a number of years in Africa with the Peace Corps, where he taught English, as well in Japan, where he taught math. Ed works right now at Catholic University as their Director of Planning and Institutional Advancement. And he co-wrote the St. Jerome Academy Plan and the St. Jerome Institute Plan, as well as many, many other things that you will discover as you talk to him. Martial arts, lots of things. Really, really grateful to Ed for speaking today about the vision of the plan, and then also to our teachers as well for speaking about the experience of teaching. So with that, any more? Ed?
Thank you very much. Thank you for joining us all tonight. Tonight's talk is going to be a little different than the kind of talks we've given in the past. I'm going to go into more detail, and I'm going to address some specific questions that we've heard about the curriculum. I want to make it absolutely clear that I'm speaking first, but with me is Ms. Mariana Narbonne, who is our head natural philosophy teacher, and Mrs. Mimi O'Hara, who is our head math teacher, not present tonight, but also involved in the... okay, Ms. Christine Bailey will also hopefully be here, and Mr. Wilbur Tain, our headmaster. We have been the primary authors of the math curriculum, the lesson planning, the day-to-day, and all that work. And I'm happy that they're here to give some testimonials about what happens in the classroom. Please direct your questions on day-to-day activities in the classroom and how students take things to them. I'm going to give you vision and planning. I'm going to begin with the structure and philosophy of math and science at SJI, and then talk a little bit about what is taught, how we teach it, and why we teach it that way. I will attempt to avoid repeating things that are already written in the educational plan, but at least a couple of quotes are kind of indispensable for explaining what we're doing. Some of what I'll talk about is just factual information, what we do or don't do. Some of the things that I'm going to touch on are things on which we have strong opinions and for which we think there is ample evidence, but also about which reasonable people could have different opinions. And I hope that'll be some area of fruitful conversation. Okay, first, I'm going to start with a list of fun facts about SGI math and natural philosophy. We teach a full high school curriculum in math and science. That is to say, we cover nearly all the topics that a student might expect to see, in a typical contemporary high school biology, chemistry, physics, algebra, geometry, and calculus class. And I say nearly because that content is by no means universal from high school to high school. And we actually cover some topics that don't appear in those programs, and we don't cover things in the order in which you might see them in those textbooks. We have homework, quizzes, tests, and labs. We believe in the testing effect, which is enhanced learning through testing. We do not teach the history of math and science except as it comes up incidentally as part of what we're teaching in math and science. We don't teach math and science in historical order. That's to say, we don't start in freshman year with Ptolemy and work our way up to the modern day. We do teach students about the philosophy of the math and science that we're studying, but that's not why we call it natural philosophy. We call it natural philosophy because we want to emphasize our holistic approach, and we take and put this in direct distinction to the modern, isolated, and largely unreflective way that science is taught today. So, what are we doing in the curriculum? SGI's curriculum is structured as a story. I'll talk a little more about why we do it this way later, but for now, I just want to tell you how that story proceeds. It will be hard to understand the logic of our plan unless you know something about how we envision this narrative. It's also easier to understand it as one story told over 4 years in multiple voices, rather than several stories told 1 year at a time. We've organized this story into 4 themes or chapters that progress and build on each other in a logical, philosophical, and theological order. This is explained in great detail in the educational plan, but in case you haven't read that yet, let me give you a brief outline. I'll focus a bit on how these chapters are specific to math and natural philosophy. Year 1, we begin with Exodus and Odyssey, moving out into the world, discovering it for the first time, discovering where we're going, how we find our way. This includes not just navigational topics, but fundamental questions of number, relation, and mapping. In this year, we acknowledge the blossoming desire of young men and women to strike out and find their own path in the world. We also acknowledge that they come from different places and bring different strengths. We start to build a shared foundation in ways that they may not have encountered before. In the second year, we continue with God and nature, where we dive into the study of creation as it is given to us. We learn to observe it and understand it without harming it. We strive to understand the material world and the organisms that inhabit it as irreducible wholes. We ask what life is and then catalog it. We watch it behave. We apply techniques of measurement and analysis to understand it as we encounter it and with as little interference as possible. In our third year, we take up the study of God and the human person and the fundamental question of what it means to be human. We begin to analyze the world in a way that fundamentally changes our relationship to it, from recipient and gift to researcher and subject. We also start to examine the world with different tools. We explore ways of modeling the world abstractly, deterministically, stochastically, and statistically. The fourth year concludes our story with God and society. We explore how we have lived together, how we have formulated the common good, the historical distinctions of public and private, the church as the city of God. We look now at human achievements that have only been possible as a society and that are revealed when we turn the lens of our attention on society as a whole. All of our seminars, including mathematics and natural philosophy, take their direction from the theme of the year. This makes them part of the story, a unique part that approaches reason and discovery in distinctive ways, but is nevertheless integrated with the rest of the curriculum. To use a musical analogy, we are striving for polyphony rather than several related songs, however individually excellent those might be. The reason for this is ultimately the fundamental unity of truth as found in our Creator. I will cite just these brief excerpts from the educational plan because it conveys this principle so well. The 4 years of study are organized according to a natural process of unfolding and disclosing knowledge, where the whole providential course of God's self-revelation to us through history is recapitulated in each human person. Since relation to God is innermost to each creature and common to all, one is always tacitly treating of God, or the world in relation to God, in treating of anything whatsoever. Theological and philosophical inquiry is the source of curricular unity, and that philosophical and theological questioning is necessarily operative inside of historical, literary, and scientific inquiry. This provides the methodological organizing principle for the core curriculum and necessitates that it be interdisciplinary. End of the quote. All right. Realizing this unity in math and science was a daunting task. Each discipline has an internal logic. No discipline maps exactly to the story we're telling. Nearly all the available materials for each discipline are self-contained and have little reference to other disciplines. However, if you look a little closer, you start to see that these assumptions aren't quite true. Take mathematics. What do we mean by internal logic? Mathematics is not linear. There are dependencies, of course, but we could choose to explore functions before or after we study geometric proof. Both vectors and conic sections depend on algebra, but we can do them in either order. Similarly, the typical high school curriculum, if you go outside of SJI, is biology, chemistry, physics. But from an internal logic standpoint, the order should be reversed. We should do physics first, which would help us to understand chemistry, which in turn would help us to understand biology. However, if you want to use calculus in physics, which for some reason we think is more important than getting basic mechanics early on, we need to wait until students are mathematically sophisticated enough to understand that acceleration is the first derivative of velocity with respect to time. Never mind that Galileo experimentally derived that without the benefit of calculus. Our aha moment came when we stopped thinking about math and science as artificially segregated disciplines and started to think of it as a unified whole for which we had 4 years of 2 periods a day. What could you do if you had total freedom to arrange all the topics logically and follow a narrative order? Algebra still has nothing intrinsically to do with nature. You can create algebra problems about things in nature, but what makes parabolas best suited to year 2 rather than year 1 or 3? In short, we can now see what we want, but how do we go about it? And so this is the how part. Here's how we did it. We looked at all the math and science topics that we wanted students to learn. We got these from the same textbooks that are used in schools today, but we added materials from a wide range of sources, such as out-of-print science and math books, materials created for college and university students that had superior treatments of these topics, online resources, open source materials, lectures, and interviews with experts. We organized all these into a graph that took into account dependencies, both within each discipline and across disciplines. For example, students need to understand linear equations before they can understand quadratic equations. But pressure and volume require only linear equations, whereas velocity and acceleration require quadratics. We then considered what math and science best fit in the theme of the year without considering level. This is an art that's not always immediately obvious, but one rule of thumb that we followed is to introduce a topic that's necessary for a modern understanding of some element of the theme as early as possible. This ensures that we don't teach an outdated understanding, though it may lack the full sophistication of the modern understanding. But it also maximizes our alternatives for future work. For example, growth and decay. They're a natural part of studying ecosystems. So we want that in year 2. They're also used in interest calculations and half-life calculations, but the nature year is the earliest we could introduce it. And the applications to carrying capacity in year 4 are pretty famous. When we had situated our wish list, we looked at the prerequisites. So for exponential growth and decay, we'll want students to be familiar with Euler's E and the natural log. But those require mastery of transcendental numbers and the logarithm. Therefore, we need to make sure those topics are covered either in year 1 or earlier in year 2. Since growth and decay comes late in the year, after we've dealt with individual organisms, we can put Napier's log in a previous unit. But we address logs themselves as soon as students study place value. The sequencing and narrative structure were uppermost in our decision process, but we also wanted to implement some key principles of good pedagogy. The first is that we want to make every effort to help students to master topics. Mastery implies that a student can call up and implement an algorithm, proof, fact, or process with minimal delay or doubt. There are some proven techniques that help make mastery more efficient. We couldn't implement them perfectly because the narrative and sequencing are non-negotiable. However, we could do a lot better than most textbooks. We build topics from year to year. In math, that sometimes means starting with the simplest form of a topic and revisiting that topic with more depth in subsequent units or years. For example, going back to our logarithms, we introduce small positive integer logarithms when we study number systems right at the beginning of year one. We know from experience that students struggle to understand the logarithm, so we start it as early as possible with simple cases where it most naturally occurs in the study of number systems. But we come back to it in year two, where we expand the study to cover the entire graph of the log function in a given base. And finally, we study it with a transcendental base e. Students study logs 3 times, with spaced repetition and with increasing complexity. Further, we've ensured that there are interleaved topics to minimize associative interference. Finally, we connected it to an actual lab and the study of ecosystems in natural philosophy so that it arrives at a moment when students are asking these questions. Now a story is starting to take shape that keeps pace with what we're talking about all across the curriculum. We're reading literature about nature. We're studying nature from the standpoint of natural philosophy. We're working with the mathematics that is best suited to that study while laying the groundwork for future math. We're studying and making art that deals with nature. We are studying history that has a strong relationship to nature, and we're even discussing nature in Latin. That gives us students the unique possibility of thinking about nature deeply, of bringing what we read and discussed in humanities to our math and science class, and to start to understand how we approach nature across the centuries and how we got to where we are today. That's the curricular how. I would also like to talk to you about how we tell this story lesson to lesson. Although if you have a specific question about how it plays out in the classroom, please ask any one of the teachers. One of our expert consultants, Jake Tawney, likes to say, in math, we start with a question and end with a proof. And that's indeed how we like to trace the arc of a lesson. The question that we begin with is typically a challenge. How can we decide or solve some problem in the real world? Is a particular hypothesis about a mathematical object true or false? This often begins, is it possible to, how many or how big? Is it always the case that, for example, the motivating question for the unit on rational polynomials, a topic familiar to all of you, is how to maximize the volume of a container with some dimensional constraints. This is a problem that we work together. Sometimes we only work a problem until we come to a point where we can go no further with what we already know. This is the point at which we stop and learn a new technique. Whenever we can derive the technique, we do. But by derive, I mean starting from known facts, definitions, axioms, or previously proven results, arrive at new conclusions or facts by applying logical and demonstrable steps. In order to maintain mathematical rigor, we want to minimize telling students that's just the way it is. Note that deriving something is not the same as randomly exploring looking for a solution. There's absolutely no evidence that that actually works. Guiding students to think about a problem includes asking them questions about what they notice or what they think they might need. When there are standard algorithms or generalized techniques for solving problems, we directly teach those. We work problems together, we give them additional work for homework. When there are math facts to learn, such as the unit circle and trig identities, students are required to memorize them. Students are also expected to be able to explain the correctness of a solution and sometimes to prove it. The combination of computational fluency and mathematical rigor work together to ensure mastery, which includes the critical ability to retrieve mathematical strategies out of context. Similarly, in natural philosophy, we begin by observing something. This could be anything from a star to a square meter of land to a spring scale under load. We then find ways to describe what we see in a controlled manner, whether that is recording the position of a star, diagramming a dissection, or measuring the time it takes for a marble to hit the floor from a given height. In the process of doing these things, we learn standard techniques for designing observational studies and experiments, recording data, analyzing data, and presenting findings. We both model and ask students to reproduce good dry lab and wet lab techniques. It is an unavoidable fact of modern science that there is a lot of content that must be memorized. We do our best to position these requirements within a broader context that links them to the other seminars, but that isn't always possible. there is really no math required to memorize muscle groups. However, that memorization comes at a time when students are studying the human person, and so provides another way of considering what it means to be embodied, which in turn informs conversations in other seminars. Our lab equipment is already extensive, and you would probably be quite surprised at just how many laboratory and field experiences we can give students. And conversely, just how few of those experiences advanced science students get at most high schools. And I'll make a little footnote here. The AP Biology curriculum says that you can have up to 25% of your time in labs, with 13 labs that are guaranteed or accepted as part of the standard curriculum. From interviews that I've had with students who are in AP Biology classes, 1 lab per quarter is the norm. We purchase and develop our own equipment for many labs, including for electric circuits, force and work, angular momentum, light, calorimetry, DNA extraction, solutions, and bioassays. And we are constantly increasing our equipment thanks to generous donations from parents and friends of the school. Our students use microscopes and telescopes, they do dissections, they look at emission spectra, and we even demonstrate the Michelson-Morley experiment with our own interferometer. So that, in a nutshell, is what we're doing and how we're doing it. And now I'd like to deliver on the promise I made earlier to give you a brief explanation for why we do it this way. I already mentioned that we make use of narrative as a means of unfolding and disclosing knowledge. It's a very powerful tool. Dr. Alexander Fleming worked at St. Mary's Hospital in London in the early 20th century. In 1928, he went on vacation and left some equipment on a wet bench, including a petri dish. He was studying the Staphylococcus bacteria, the same bacterium that causes impetigo in children. You see where this is going? Do you want me to finish? Yeah. Okay. He found that some mold had started growing on the petri dish, and where the mold grew, the bacteria didn't. He investigated and discovered that the mold produced a self-defense chemical that killed staph. He called it penicillin. All right, so the salient point, Fleming discovered penicillin in 1928. But if I had just told you that fact and hadn't filled in the rest of the information, I argue it would actually be harder for you to remember that fact than it is with the story, even though the story contains many irrelevant details. I could have filled in other facts, like Fleming's experience as a British medical officer in World War I, and that would have helped you to narrow down the date that this happened. Humans can organize and retain an enormous amount of information if it is communicated as a story. Think about all those Lord of the Rings nerds who can recite Tolkien's poetry and give you obscure elven lineages. How many of them can also recite the first 10 U.S. presidents? If they can, they most likely know them because they memorized a list in U.S. history class and they drilled on it over and over until they got it right. Pull one of those presidents out of context, though, and say, the president during the Panic of 1837, and fewer can name Martin Van Buren, but now you'll probably never forget it. And now you're probably wondering what the Panic of 1837 was. The second major tool we use is seminar format. Seminaring is a way of helping students learn how to ask good questions, how to be precise, and how to collaborate with their peers. Seminar leaders provide sufficient guidance and support to help students arrive at understanding and to apply their knowledge in creative ways, but also challenge students to think carefully and deeply. You probably already know that seminars are a staple of our humanities program, and the educational plan talks about the seminar method and the content covered in depth, and so again, I urge you to read it. We also teach mathematics and natural philosophy in the seminar format, but this differs somewhat from the discussions of texts or works of art. Students may still prepare for the seminar by reading a text. This is very typical in natural philosophy, a little less so in mathematics. In both seminars, the teacher helps draw students' attention to the overall story. Why is the text structured this way, and how should we expect its information to be organized? What can we tell about the problem and what kind of solution we're looking for? Learning how to approach a topic in this manner is just as effective for a reading on angular momentum or electric charge as it is for discussing several chapters of the Aeneid, but it's adapted to the needs of math and science rather than literature and poetry. You can just give students a formula for solving quadratic equations, and you can drill them on how to use it until they can recognize the quadratic and give you the real roots immediately. But without its story, without building up to it through factoring polynomials, until they really long for a closed form solution, it remains just a disconnected math fact, and one that they're at risk of misapplying later on. These two tools, narrative and seminar, are the foundation of our approach because of their effectiveness at unfolding knowledge. I mentioned earlier that we implement good pedagogical techniques whenever we can, as long as they don't interfere with the rhythm and connections we're making in the narrative arc. There is strong evidence that gradual complexity, interleaved practice, and spaced repetition work at the K-8 level, and many good programs like Saxon and Singapore use them. So one wonders why contemporary textbooks abandon these tactics at the high school level and require students to just buckle down and learn the material. But even university math and science teachers are starting to recognize that these are lifelong learning strategies that help us to manage cognitive overload, promote transference from short to long-term memory, train recall, and avoid associative interference. We are constantly revising the curriculum, even within the school year, to improve both our methodology and our technique. And our structure gives us the flexibility to do that in many ways. And I actually have a 4-page map for you that I'll hand out after. This is hot off the press, the 2026 version. What's the first thing that happens when you print out 30 copies of something?
You want to make a change.
What?
You want to make a change.
You find a typo. But I would like to conclude my remarks with a few questions that I think address some of the biggest concerns that I've heard about our approach. I don't intend by this to preempt a conversation about these topics, but if I can provide a little clarity around the bigger issues, we'll have more time to talk about the specifics. First, I get this question in a lot of different ways. Sometimes it comes in the form of this or that text or curriculum. What do I think about Life of Fred or The Art of Problem Solving or Navarre? And sometimes it comes in the form of what I think about how the Heights does things or how Exeter Academy's approaches or Trinity System. And I boil all these questions down to what is wrong with teaching math and science the way everyone else does? And that makes me wonder, because that question is being asked by everyone today, educators, researchers, politicians. STEM literacy has been declining overall for decades. In a 2015 study by the National Institutes of Health, the STEM degree completion rate in U.S. four-year colleges was found to be less than 40%. That doesn't mean the graduation, that means they transfer out of STEM. And true, we have an elite percent of a percent that do amazing work in artificial intelligence, the space industry, nanotech, advanced cancer treatment, and so forth. And I suppose you could say for those students, the system is working as designed. But what about everyone else? We all want our children to go on to be well-educated and have an opportunity to work in these fields if that's their interest. Do they just need to work and try really hard? And just to be clear, if your son or daughter isn't spending a lot of Friday nights home alone with a math and science textbook, they're not graduating summa from MIT. The competition out there is very, very steep. But maybe there's some way we can just extract the good parts and then provide a few additional supports and then just do that. Well, let's think about what that part looks like. It's not the unedited content. That's permeated with the materialist assumptions of its authors. And it's not the techniques. High school course structure precludes interleaving among sciences, and no textbook I've ever seen has used spaced repetition or gradual complexity. Their sequential building units actually risk significant associative interference. They rely almost exclusively on repetition and rarely teach out of context. If there's something out there that's really working well that we haven't implemented, please tell me about it, and I mean that sincerely. The second general question I get, which is typically formed as an assertion, is how rigorous is SJI's math and science? Now, I get that most people don't use the term rigorous in the way a mathematician does. So as a public service, I'll just mention that to a mathematician, rigorous means precise, logical, sound, and thorough. It's the difference between saying, if two numbers share a common factor, then their sum also shares that factor, and saying something like, let n and m be natural numbers sharing a common factor a, such that m is not equal to n, et cetera, right? By this definition, SJI's math program is far more rigorous than most high school textbooks require. But let me address the intention behind this question by first investigating what most people mean when they say a program in math or science is rigorous. Typically, they mean it moves quickly, covers many topics, and gives a lot of homeworks and tests that include progressively more difficult problems, some of which will only be solvable by a few students. Many students can achieve success in these programs because they have very good recall and study habits, they have good pattern matching skills, and they can pick up the skills needed to recognize a solution on a standardized test. Much of that knowledge will melt over time, but the general attitude is that students can relearn whatever they need later. The objective is just to show that they can succeed in that kind of an environment. Well, you know what they say about law school. It's a pie eating contest in which first prize is more pie. So if you win at that program, then you move on to even harder programs where you're asked to do the same thing. So what's SJI's answer? We actually want more. We don't want knowledge that melts over time, is isolated and locked into its context, that discourages creative and deep thought. This additional rigor that some people are looking for is trivial to layer on top of an excellent education, and most of it won't cost you a cent. What you cannot easily get, even if you're willing to pay for it, is the educational experience that we're building for our students at SJI. Which means I do need to address the SAT, the ACT, the CLT, the AP, and college admissions in general. Success on standardized tests requires preparation. That's it. That's the whole formula. The entire AP system is predicated on classes that prepare students to take one test. They spend a year memorizing, drilling, and doing sample problems, and then they take the test. The SAT is a little better, but a prep course such as the one that Ms. Bailey is currently teaching remains the gold standard for a good score. Our curriculum delivers all the content that students need to know to do well on the math and verbal portion of the SAT by early spring semester of junior year. The rest is just learning to recognize problem patterns, recognizing tricks and gotchas, and then practice, practice, practice. College admissions is admittedly a harder pill to swallow. Most universities have dropped application fees and have started to accept the Common App, so applications at all the Tier 1 institutions have skyrocketed. Our children are dealing with a very different higher ed landscape than we did. I'll just give you one example. Notre Dame accepted just over 9% of its 35,000 applicants for the class of 2029. Their composite SAT score was 1,500, 740 verbal, 760 math. I want to read to you, though, from the 1983 admissions bulletin from Notre Dame. The quality of the undergraduate student body is outstanding. The class entering in the fall of 1983 was chosen from 6,293 applicants for admission. Of these, 2,829 were admitted and 1,786 actually enrolled. The average SAT of those accepted was 1202, verbal 656, math 637. Of those actually enrolled, the average score was 1188, 557 verbal, 631 math. So that's an admission rate of 45% in 1983 as opposed to 9% today. That's 5 times higher than the current rate, right? So UMD College Park is called a public Ivy by Forbes. They had 65,000 applicants for early action, and they denied half of them, over half of them. So combine this flood of applicants with the decline of things like legacy admissions, and I can definitely sympathize with the desire to get high scores. But I still believe we're better off distinguishing ourselves through integrated and comprehensive education, by preparing students to be better speakers and writers, and by layering on supplemental support for the gateway tests. So those are the 3 big questions that I get all the time. I'd like to now just open the floor to my colleagues. I don't know who wants to go first, but just for some of their remarks on their experiences in the classroom, what they see with students and reactions, and then we'll open the floor to questions.
All right, I'll go first. Again, I'm Mimi O'Hara. I have been here at SJI since we opened 6 years ago, and this is my 15th year teaching high school mathematics. The first 2 years were in a co-ed Catholic school in Los Angeles, a pretty rough and tough but beautiful place. And very computational based in mathematics. We actually had a program that was essentially Khan Academy, but on paper. So very, very computational. And then I spent 7 years teaching at an all-boys high school in the DC area. And I was really excited when I was hired because I knew both from experience of student teaching, but a little bit from that experience, but just also just from the sort of the how people spoke about the school, that this was a group of very intelligent young men who were very academically capable, who generally came from good schools. And so I was really excited to have the opportunity that meant that computationally they would be so quick with everything that we would have time to do the more interesting and the more fun and the more really explain and go deeper type of thing. And the language that you hear from a lot of schools is that is something that happens. But the reality is that it can't happen when the focus is on, as Edward was saying, this very stepwise computation. You can't do this type of equation until you've shown you have mastery of this other type of equation. And we need to do a whole several days of one-step solving equations before we can do two-step solving equations, before we can do multi-step solving equations. And so it's just this idea of again, as Edward was talking about, that there's not room in general, there's not space in the curriculum to slow down and say, whoa, you, student A and student B, you have two totally different looking answers, but you both got the same thing. Why did that happen? There's not really a lot of time for it. And in fact, it's the idea, again, from my experience, the idea was so foreign to some students that could even be something interesting or something that we should talk about. It was actually kind of frustrating for some of them. I had an honors Algebra 1 class where this happened. And it was really frustrating to them that I tried to spend 10 to 20 minutes talking about what happened in the solutions that they looked totally different but got the same answer, because they just wanted to know which way they were supposed to do it and which was the right one. And so then coming here to teach, frankly, I was mostly coming here because I wanted to be able to teach part-time, and I was looking for a place that I felt was more in line with the way that I live my Catholic faith. And I knew things about the math program, and I knew it was going to be more of what I wanted, but I didn't realize how much so and how much I was missing. Teaching these computational things, you can kind of come up with ways to make it more interesting or to make it to apply to a certain topic, but at the end of the day, when it's just more quadratic equations, or it's just, and that's, I like those problems, so that's fine, and I was getting kind of bored because I already solved all the quadratic equations from this book, so I guess I could find some more equations, but there's just more quadratic equations. And whereas here, even just teaching here, I've just learned so much more about what a quadratic equation is, just ideas that I never would have come up with before. Like, the thing that I'm still sort of processing and trying to figure out and roll around with is that some of the addition and subtraction and multiplication division you do with quadratic equations works because it's essentially it's almost exactly like a number in base value. I mean, I didn't even study base value or place value that much, besides when I was, 5, until teaching here. And for me, I could solve all of those problems. And again, as Edward was saying, I'm somebody who, the pattern of it, the logic of it, it makes sense pretty quickly. So I could just do it. But I didn't. But besides some kind of the line of, polynomial division works because it's just like a number, and a polynomial is essentially a number because you could plug a value in for the x. So it's just a number, so it works like a number. But I could tell you that line, and I taught that line, but I didn't understand what it actually meant until I started teaching here. And I think you'll hear that echoed in some of the other experiences. And so I find that what ends up happening is, for the students who come here who would say that they're bad at math and it's hard for them, they begin to realize that there's actually a lot that they can do. It's not that they're bad at math, it's that they're bad, or maybe they're not as quick at putting those patterns and those puzzles together. And that there are some ways when actually, especially when it comes to writing out proofs and really understanding the way to write a good proof, that they're actually better than some of their classmates who have traditionally been good at math. And similarly, I think it's so important and so good for our students who have gone through saying, I'm good at math, to have a different kind of challenge. Because, again, as Edward is saying, you're going to give them more problems, and it might take them a little longer, but eventually they're going to be good at it again. But where they struggle is to understand the why. And I think what's important for me, especially with our students who are really quick with computation, is that in order to do good mathematics, you sort of have to approach it humbly. You're not going to be able to discover something new or make it through a really, really hard proof or some kind of new discovery. You're never going to get your doctorate in mathematics if you're just good at computation and you feel like you just know it and you always and so to really push them to understand, but also to have that humility that there's a bigger picture here. There's a whole field of mathematics that almost has nothing to do with numbers and computation. And it's really interesting. And in order to do good mathematics, there's just so much more there than just the problems. So I'll stop there. I could go on, but
that is great. I love it. So my name is Mariana Narbon, and I'm the natural philosophy teacher here. This is my 4th year teaching, and this is my first school I've ever actually really taught. I taught in a school in Philly, but it wasn't really teaching. I was just babysitting basically. So this is my first teaching job. So I have a background in science. I studied neuroscience at UPenn, and even in high school I loved science, but there was always something that was missing. And when I went to Penn, I loved it. I loved studying all the things and all the parts, but every time I would ask a question, I would just get the answer, what do you mean? It's just neurons. What do you mean? It's just a kidney. It's just how it works. That's what it does. And I was very disappointed after 4 years at a school that I thought, was going to give me all the answers that I was searching for, that I didn't get any answers. I just knew how things worked. And I just memorized it, and I knew it, and it was interesting, right? I always say that I love the kidney because the kidney just works on its own. There's nothing, it's just gravity, and it's just amazing, it's beautiful. But that was not what I was taught, right? It was just very this is how it works, this is what things do, and that's it. So I kind of threw science out of the way, and I was I'm gonna do theology and philosophy because, I'm gonna get answers. So I went to JP2 Institute here, and that's where I actually came back to the sciences because it was really beautiful that there I was able to see that what I was missing was the what is question. I really did not know what a neuron actually is, what the kidney actually is. And then when I came to teach here right after I graduated from the JP2 Institute, we were talking to Ed about it when we were talking about the curriculum, and I realized that what we do in natural philosophy is ask that what is question, to really show the students what the world is, what they're encountering, what nature is, in a beautiful narrative that for me has been all the answers that I've been asking all my life. Now I'm discovering with the students. It's been really beautiful for me. It's been very, redeeming of science for me because I'm always, every time I teach, I'm you guys don't understand. This is amazing. And they're yeah, okay. Calm down in a second. But it's really beautiful because for me, I'm for the first time, I feel I actually know what the things that I'm studying or the things that I'm teaching in this sense. I guess I'm studying with the students. So yeah, the way that the whole natural philosophy curriculum is, Ed said, is 4 years of kind of looking at the same mystery from different angles and going deeper and deeper into it, which I think it's just the way that reality is. The way that I explain natural philosophy usually is when we're studying a bird that's flying. It's not physics is happening now, and now biology, and now chemistry, and now navigation, all these separate things, they're all happening at once in the bird. So the way that we approach science here is that's what we're doing. We ask the what is a bird question, and with that we start looking at all the different ways in which the bird is this. So of course this physics law is applying here, and this chemistry is applying here, and the biology is here, but it's because of what a bird is in a sense. So what reality is, what the thing that we're studying is, and I think it's fascinating to see the students. One of my favorite things is when I teach all 4 years, so I go with all the students now. My seniors were the ones that were my freshmen, so I've gone through all 4 with them. And they remember and they go back and they're like, oh yeah, that was what we talked about freshman year when we talked about navigation. Now we're doing this thing here in fourth year, and I can see it. And one, I'm always like, they were listening. This is great. I love it. This is awesome. But also, I stand back and I'm like, look at the beauty of the curriculum that we have here, and how the narrative and the story really helps in their understanding of the world, which I think is just key, and who they are also, because they're taking part of this creation of the world they're in. So I think it's great, and I love the fact that whatever they're doing in math or in theology even, or in humanities and Latin, we all kind of are doing the same thing at the same time, really beautifully. Yesterday with my seniors, we were talking about Alan Turing's imitation game, AI, and we're discussing the question, can machines think? Are they able to think? And we did it for 2 days, and every single time we were going through his objections of why his position is that they can't think. It was impossible to get through the objection without them coming to the question, well, but he doesn't tell us what thinking is. So if we don't know what thinking is, then how are we able to really deny or affirm his position here? And I was like, that's all I wanted you to say. I was like, great, we can go home now. Yeah, it was beautiful because they really had a really lovely discussion, and we closed, like the bell rang and they sat up and they were like, that was amazing. Okay, now to humanities, to the same thing. And I was like, that was so great, because now we're gonna go to humanities and discuss the same thing from a different perspective. So I think it's just, or even today with the freshmen, we're talking about the law of conservation of energy, and I have a Newton's cradle, so I can do the whole, going into Newton's cradle thing. And I was okay, so if we're talking about the energy is not created or destroyed, and I'm adding energy to it, why does it stop? Where does it go? And they were going over and over again, and I was asking questions, and they were coming up with their solutions, and then they understood that it's still energy is conserved somehow, even though it's giving us heat or friction or whatever it is. But it was really beautiful to see them just really struggle with the question, if this law is true, then what's happening here? What is it that is happening here? And it's something that I never had in high school, and I really yearned for it. I was very sensitive to it. And here, as Mimi said, I'm never bored, because there's always something new that I'm discovering with the student, right? It's really beautiful to see their questions. I had a student ask me if I get bored, because it's my 4th year teaching the same thing freshman year, and I was like, it's impossible, because you guys are participating in the class in a way that you guys ask questions that I've never thought about before, no one has ever asked me before, and we can come to answer together, because it's a truth that we're aiming towards. It's, as a teacher, I think, like I said, I've never really taught anywhere else, and I think I'm lucky because of that. But it is something that I never expected it. Of course, I've seen teachers in my life, so I never expected to have this experience of continuously learning and continuously being wrapped up in the sense of wonder that the class has because of the beauty of the curriculum and the narrative, and also just seeing it in the students, how they light up when they finally understand something, or they have questions, or they just sometimes they have a million questions and have to be okay, wait a second, let's get one at a time and we'll see how we can answer. Sometimes they get really frustrated when I'm like, next year we'll talk more about it, and they're like, everything's next year, and I'm like, no, but I'll talk to you a little bit, so you're you come back. No, I'm kidding. It's great. It's really I love it. I think it's really beautiful to see, and it's just been really good talking to alumni, or to a student that's not here, and he's not graduating from SCI, he went to another school, but he remembers what we did freshman year. Every time we talk, he's like, oh yeah, we did that calorimetry when we used the salt and we measured the difference because we're studying energy. So and I'm like, how do you? This is great. I did not think you were thinking and remembering, but then you are absorbing and having this beautiful sense of wonder. So for me, that's the beauty of the natural philosophy curriculum. That is exactly how I would have wanted to understand the world, to have that sense of wonder. And I'm just really happy that our students are able to discover the truth about reality and about nature this way. Yeah.
Christine?
So my name is Christine Bailey. I also teach math here. This is my third and a half-ish. Yeah, and I think my background is I'm from the area. I went to Eleanor Roosevelt High School. I was in the Science and Tech program. I went to University of Maryland, and I studied computer science. And then I worked as a computer scientist for a little bit for the DoD. And I was always good at math, and I thought I liked math, but I really just like knew how to get the right answers, and like I couldn't really tell you much about E except it's just that number 2.7ish that we just use it because it's there. And I think like my entire education was really just like, oh yeah, just know how to get the right answer. And then like even like working at the DoD, well, I'm just like solving problems. I'm just gonna make this thing work a little faster, but. I don't know. Yeah, I never like considered to ask like, what am I doing, and like, what is this, and what is an integral, or what is any of it. And I never ever considered like that I would be able to study mathematics because mathematicians are geniuses. Like I couldn't do that. But then I started out just as a long-term sub for Mimi, and I stayed on because. And first of all, teaching is so fun, but it was really incredible that by teaching math, I thought I knew it, and then I got to like do my lesson planning. I'm like, oh my goodness, like what? I didn't know that's how it worked. Like it was really, just so incredible to see. I mean, like the other, like we just started learning E, like Euler's number with the sophomores, and just like its slope is itself and why. And like they're talking about like slope, which is not something you would do until you get to calculus, but like they're already investigating it, and so that way when it gets to calculus, they're like, oh yeah, I remember that thing. Which actually the seniors we're just doing the natural log, which is the area underneath 1 over x, and they're like, oh yeah, remember that thing we did sophomore year where we like cut up the areas and added it up, and I was like, yes, that's why we did it. So it's great to see that they're putting the pieces together, but it's also great for me, like I've fallen in love with math, and like and I think that by studying here at SJI, it's actually preparing our students to be, if they want, to be a mathematician. Like at Roosevelt, I could not be a mathematician coming like out of high school. I didn't understand anything what I was doing. I couldn't prove anything. I could just get the right answer. But here, the focus is so much on the proof. I mean, the computation, you need it. And so we do like drills, right? We do lots of homework, but like that's part of it too. But with being able to look at like what's going on behind the scenes and how did these, like these equations that we're using, how did they get derived? And then them practicing their derivation skills. I think that's allowing them to pursue that after high school, if they want. And if they don't, it's fine. Now they have this, but now they know how to think better. I think even that is an addition. But I know you probably have questions, so I'll just stop there and then open it up and help.